In lesson 3, we're going to be doing a lot of different calculations that involve compounds and also chemical reactions. The first thing we need to do is to introduce another unit of measurement for quantifying the number of particles, atoms, or molecules. We need this because if in chemical reactions don't occur in terms of mass of reactants. They occur in terms of numbers of molecules or atoms. 3 carbon atoms react with 3 oxygen molecules to make 3 carbon dioxide molecules. Those ratios are important. Anyway, so we're going to first look at the individual molecules and coming up with a way to count them and weigh them. First, let's look at something simple called the molecular weight. The molecular weight is just the mass of everything in one molecule, one individual molecule. And we measure that in AMU, at atomic mass units. The formula weight is just the same thing. It's a more general term because technically the word molecular weight has molecule in it, which means it's a non-metal compound. So formula weight, we would say, is more inclusive. It includes both ionic compounds and molecular compounds, just based on the formula. So to get a molecular weight, we're just going to add up numbers off the periodic table. We're going to use the atomic weights on the periodic table. Let's try an example. So to get the formula weight or the molecular weight, either one, you just add up the atomic weights in the formula. Remember, the atomic weights are found on the periodic table. The periodic table is numbered according to atomic numbers, the number of protons. The other number on the periodic table is the atomic weight, and we're going to be using those. So to get the, we'll do a molecular weight. For this, here's 1 molecule of H2O2. This is hydrogen peroxide. Anyway, I'm going to take 2 times the 1.0 for hydrogen plus 2 times add that all up. And that means the mass of 1 molecule of H2O2 is 34.0 atomic mass units. Notice when we're doing a molecular weight, we're using the add rule. So I just pull my numbers off the periodic table with 1 decimal to the right of the decimal, 1 place to the right of the decimal, and then it lines up that way. If you're doing something that needs more sig figs, you'll need to use a periodic table that doesn't round them off so much. Okay, we're going to do another example, and I think we can just fit it right here. So what we want to do, let's do another example. Let's look at sulfur dioxide. So some review here. I need to get a formula in order to do a formula weight. Sulfur and oxygen are both nonmetals, so this is just a molecular compound or covalent compound. I just use the prefixes to tell me that it's SO2. To get the molecular weight, I'm going to look on the periodic table. This is sulfur plus 2 times 16 for oxygen, 64.1 AMU. So that's the mass of 1 molecule. I'm going to point out something here that I didn't before. Why is there a 2 here? It's because there's 2 oxygen there. So when you're adding these up, make sure that you're multiplying by the number of each element in one molecule or on one formula. We did that practice. Okay, well, the reason that we need to count them is because reactions occur in terms of numbers of particles. When we look at this reaction, we have a decomposition of water. We read these coefficients, these numbers in front, we could read them as this is 2 molecules of water, splits apart and forms 2 molecules of hydrogen, and there's an implied 1 here, isn't there? So 1 molecule of oxygen. Okay. So we need to keep track of the numbers, because what if we wanted to say, well, how much hydrogen could we make from this much water? We can't count these molecules in the lab, so we need to get a kind of a trick to do that. And I'm going to use an analogy to explain our trick. True story. My father-in-law likes to collect things. He collects a lot of things, but one of the things he collects is change, and he sorts his change, and it's in jars, really. So once my mother-in-law decided, I'm going to cash in some of all these dimes and other coins as well, because this is a lot of money here. So they were going to count them and see how much money it is. I don't know why they didn't just take them to the bank first. Don't ask me. But anyway, so they're going to count dimes. My husband was helping her, but there are an awful lot of dimes. And so what they did is they played a little trick. Instead of counting all the dimes, they counted out 100 dimes and then weighed them. She had a little scale, like a Weight Watcher scale or something, and they weighed the dimes. So they found that 100 dimes had a mass of 0.052 kilograms. Okay. Once they knew the mass of 100 dimes, what do they do to count the rest of the dimes? All I have to do is weigh them now. So let's say they weighed them, and without jars, they'd have to subtract out the jar mass. Okay, so say they got 1.04 kilograms of dimes. Well, then math-wise, what do we do? How many dimes is that? And maybe you can just look at that and know whether you're multiplying or dividing, but I'm going to set it up as a conversion factor. 1.04 kilograms and I don't want kilograms, I want dimes. So kilograms will cancel, I'm going to dimes. And then my conversion factor, is this. So for every 100 dimes, I know it's 0.052 kilograms. And so then we could figure out, and I'm going to watch my sig figs here, how many dimes. Okay, so this is a good analogy because it shows you how we can use a balance to get a mass, and then use a conversion factor to figure out how many we have. Okay, a couple of things. So this is our conversion factor. We're going to want this for atoms as well, which we will get. But anyway, a couple of things that are important. First of all, do all dimes really have the same mass, or do some dimes weigh more than others? They really do vary, because over the years they've changed the composition of dimes, and so some are more heavy than others. They used to be pure silver, and now they're definitely not. So they don't all weigh the same. They don't all weigh the same. Does that matter? Does that affect our conversion factor? No, as long as we make an assumption. Our assumption is that the dimes are well mixed, that we don't have like one jar of really old dimes that have a different mass than another jar of newer dimes. We're assuming that they're well mixed and that the 100 dimes that we counted out was a representative sample of the dimes. Okay, so that's important. Another thing, if I wanted to count quarters, could I use this same conversion factor? No, I would need a different conversion factor because quarters are heavier than dimes, and so it's going to be a different number for, it's going to have a bigger mass here for quarters. Okay. This is exactly what we do with atoms. We come up with this conversion factor for each element. It's different for bigger atoms than it is for smaller atoms. And in each case, the conversion factor takes into account the different isotopes of that element. So we assume that our atoms are well mixed throughout nature so that when we go to count them, we can use that average mass per number